on demography, and that's really looking at the stats of population size. And I don't know how aware you are, but last year we did the census in the United States, done every 10 years, and not done well. Lots of people don't participate for various reasons. And one of the problems is California, the first time in a very long time, we actually lost a representative. It is thought that we were probably undercounted. California is not growing, which probably is a good thing. But yeah, so anyway, we have lost a representative, and Florida, Texas, and some other states have actually gained some. And so in the political process, maybe California has lost a little bit of its influence. All right, so let's take a look at, get off of politics and actually take a look at the way biologists would look at demography. And you're looking at life tables. Each species has a life table, and you're going to notice this is the life table for the female, because males don't matter. And they do matter, obviously, but reality is they are sperm donors, and it's really the females and their ability to have young that is determining population size. And so there we're looking at a ground squirrel here, Belding's ground squirrel at the Tioga Pass, over up by Yosemite. And so what they're doing is looking at, how many are alive at certain ages, proportion alive at start of year, and then the death rate and the average number of female offspring per female. So all of this has lots and lots of information in it. And what you're seeing here is the ages, lots and lots of babies, very few living to the age of 10. And so kind of where's the sweet spot? Where are they having kids? The kids are, survival rate is probably 4 or 5, starting at 2 or 3, going until about 6, and then the rate starts to drop off as we go. So that's all important when you look at population structure, and we'll show you that in just a minute. Okay, so and there's what we call survivalship curves, and here's the Belding ground squirrel, and lots born, and then as you get older, you can see it just kind of drops down. And this is a log scale, so it's not really linear like that, but anyway, so this is one of the 3 that you'll actually see. Humans, on the other hand, is type 1, where we have lots of babies and most of them survive. And then we have very few people who live over 100 years old. So you can see it kind of drops at the old age very quickly. Whereas you have on the bottom an oyster, and an oyster you can see thousands are born, and they not many make it to a big age. Now there are some very, very old ones that kind of survive, but they kind of bail very quickly. So although there's lots and lots of babies, lots of them don't make it to adulthood. All right, so what we're going to do is look at population growth and look at how things grow, and we're giving you 2 theoretical types. One is exponential growth, which is the one we're talking about here, and then the next will be the logistic growth, which we'll talk about in a minute. Okay, so exponential growth is often called a J-shaped curve, and because the growth looks like the letter J. And I want you to know the formula. dn over dt is equal to r max n. So dn is actually delta n, which is the change in number over the change in time. And n is the number of individuals. And then r max is what we call biotic potential or intrinsic growth rate. It's really how many kids can you have? What is that number? And all species are different. There are some organisms that can have thousands, and then humans quite a bit less than that. So and if you think of things what breeds quickly, people think rabbits and rats. They have a higher R max than maybe humans do. So to kind of give you an idea. So exponential growth. So things that do this are often weeds. Yellow mustard would be a plant. Bacteria is a good example. Actually, cicadids, which should be exploding soon, another group. They're on the 7, 9, 13-year cycle, 11 cycle. There's different cycads at different levels, but anyway, so that's exponential growth. The other type of growth is logistic growth. Again, I want you to know this equation also. What you're going to notice, the equation very similar to the first one, except for we have this extra symbols on the end, k minus n over k, and that is called k is called the carrying capacity, and that is how many individuals can a habitat sustain. And so what you see is it's not a J-shaped curve anymore. This is actually called S-shaped, or sigmoidal is another way, but S-shaped is typically how it's talked about. So by carrying in that carrying capacity, as you get closer and closer to the carrying capacity, you start to level off. And this is actually done by large terrestrial mammals, things like lions, tigers, bears, and lions. So, all right, and so if you look for logistic growth up on, everything, paramecium population in the lab, if you have a test tube with only a certain amount of nutrients, it is going to hit a carrying capacity. And you can see Daphnia now, and what we're trying to show you here is paramecium will actually slow down and kind of follow what the food will allow. Whereas Daphnia, on the other hand, will shoot way up and then overpass, and then obviously they have a die off because there's not enough to support it. And then they kind of level off of it. And then there's other animals like song sparrows in the natural habitat where they're all over the map, and it might even be hard to tell where their carrying capacity is. And that can be due to all kinds of different factors, sources of food a certain year, amount of water, could be a catastrophe that happens, fire, something. So all kinds of different issues. With that, we'll stop the share.